Hi, folks. We have a lot to talk about this week. Um, Something on the order of like 3 chapters. It's not the first week we've done that. We covered 3 chapters back in the first week of the summer, um, but it's a lot. So I'll post videos kind of on a rolling basis between now and early next week, so that we aren't overloaded with a whole pile of video segments all at once. Uh, so I'll post the first couple segments on Friday evening, the 29th, and then other videos will sort of populate over the weekend, so that we can kind of ease into things. The the other reason this particular week is notable, up until now, we've been covering chapters pretty much in order. We started with chapter 1, and then chapter 2, and then chapter 3, and then chapter 4, and there was like a little bit from chapter 3 that we had to look backwards and get. But basically, we've progressed in order from 1 through 5, and I think there were good reasons for doing so. Not just because that's the order in which they're printed in the textbook, but because it makes sense, in terms of putting concepts together and synthesizing vectors with kinematics to get 2 or 3-dimensional motion in chapter 3. There's a progression to it. The authors of the textbook have good reasons for presenting the next few chapters, 6, 7, and 8, in the order that they do, or at least for presenting the material in the order that they do. But I have done this several semesters in a row, and I've had good results covering the material in these chapters a little bit out of order. There's a thing that we do in chapter 6, a definition that we make, that doesn't really, it's not clear to me why we make it, except that we need to. And that's always kind of bothered me. That I really want to know what prompted us to make that definition. Like at a certain point, okay, you tell me to make the definition, I will, and I'll call it whatever you want. But I still kind of want to know why that? Why are we assigning this variable to this particular expression as opposed to something else? And the answer lies in chapter 8. So I'd like to start this chunk of material, these 3 chapters. I'd like to start it in chapter 8 and tease out some pieces from chapter 8 that we're able to talk about now, move from chapter 5 right to chapter 8. And then, based on the things that we encounter there, take a look back and really dig into why we need chapter 6. And then we can build a sort of a logical progression. If we have 8, then we need 6. And if we have 6, then we need 7. And then once we have 6 and 7, that informs the rest of, so it sort of fills in the gaps between what we started with in chapter 8. We can fill in the gaps and get a full picture of 6, 7, and 8. So I apologize. I'm going to have to jump around a little bit between chapters 6, 7, and 8, but I think it's worth it conceptually. I think it builds a better picture, builds a better house, than it's better laid out than if we just strictly follow the textbook. On a certain level, the textbook exists and we could follow it, and that would be fine. But part of the responsibility, I guess, part of the job of an instructor is to position the materials in perhaps a different way, another way to access the material. Um, maybe maybe it's a good idea to read or at least skim through chapter 6 and 7 in preparation for what we're doing here, and maybe that is a you know a structure that makes sense for you. But it might also be true for others of you, or for the same folks, that the configuration that starts with 8 and then goes back to 6 and 7 makes more or different sense. So I think I'd do you a disservice if I didn't at least explore it. Cool. Let's dig in then. Let's start with Newton's second law. The acceleration of the mass m is the time derivative of its velocity. Now, what if this is a particle, some object, right? If it's a cart on a glider track, or a marker, or I don't know, a rock, something, some object, its mass doesn't change, which means we could have written this. I mean, if the mass is constant, then we could pull it outside the derivative and we'd end up with this again that we had before. So this could be the result of pulling the mass out of the derivative operator, because we know that it is constant. But if we write it this way, it starts to look like this is the time derivative of some new thing, some new quantity that is the product of mass and velocity. I mean, suppose we define three line equals is defined to be some quantity p that I'm going to call momentum. Suppose we define a quantity, momentum, as the product of mass and velocity. Well, I mean, we could make that definition, and I think we are pushed, nudged to make that definition because we wrote this expression. This looks like the time derivative of thing. If we define thing, it looks like there's some quantity there. And it has a lot to do with motion. There's what object is it, how much matter is there, and how fast is it moving. So this quantity does a pretty good job of telling the story of motion, how much matter is moving and how much is it moving. I think it's a good idea. I mean, I think it's a reasonable thing to do, at any rate, to make a definition. Whatever we call it is fine. Whatever symbol we use, okay, fine. But I think it's worth sort of singling this out as a new quantity, something that we can look at and see how it behaves. Maybe it turns out to not do anything useful for us, which it might not. But maybe it does, maybe it does turn out to do something useful, in which case, yeah, I'd like to have defined it, given it a name so that we can work with it as we go. Okay. So let's see. Okay, so the units for this new animal, it has the units of kilograms times meters per second. And in fact, that's the unit that we'll use to talk about momentum. We don't have a sort of a nice packaged unit like newtons for momentum. It's just kilogram meter per second. The symbol P is it's a little bit of a we're giving a little bit of credit to a researcher who was looking at describing motion at about the same time Isaac Newton was, and had sort of built this framework that described motion in terms of two quantities. The researcher's name was Hamilton. Hamilton hadn't really worked out what the two quantities were, like what their identities are, but he was calling them P and Q. He was just using them as letters to track the fact that one was one variable and the other was the other. His variable P turned out to be our variable momentum. So even though we're still sort of framing this in a Newton's second law kind of way, we'll use the symbol that Hamilton did as a little bit of a, hey, we see you, you were there with the band. So that's why the symbol P. It's not because momentum starts with P. It doesn't. But it's the symbol we'll use. It's a lowercase p, and it does have the vector ornament because we're multiplying a scalar mass and a vector velocity. So the right-hand side is a vector. The left-hand side is as well. So all of the vector calculus that we've been talking about so far still applies. And it is vector calculus because if we rewrite Newton's second law this way with our new definition, we're talking about the fact that the sum of the forces acting on some object is the time rate of change of the momentum of that object. Cool. That's sort of a neat statement on its own, that momentum is a thing that does the job of telling us how much motion, right? How much stuff and how fast. How much motion are we talking about? And we're expressing the change in how much motion as the net force acting on that object. So it's sort of like we're switching the causality around. When we look at F equals ma, we think about the forces and how they are causing the acceleration. That it's a forward causality, I guess. Here are the causes, what will be the effect? It's predictive in a lot of ways. But in this configuration, we're talking about here's the motion, here is what's going on. I observe the results. What was the cause? So it's descriptive in a way, analytical, right? Here is what happened. What must have been the cause for what happened? Well, an object's motion changes if we look at Newton's first law according to the net external force acting on it. So it's the same. It's Newton's second law. We just wrote it with a derivative instead of with acceleration. But it does sort of change the flavor a little bit. Speaking of differentials and flavor, let's start with this modified version, the differential statement of Newton's second law. If we treat this, well, like it is a differential equation, it's a differential equation that is separable the same way that the differential equations we looked at when we were talking about air resistance were separable. What if we put dt, what if we multiply both sides by dt so that we can write this? That makes me think we can integrate. So the force, the net force that acts on this object might be a function of time. It might change in time. In fact, we've already talked about one. Air resistance changes as a function of time if your velocity also changes. So there's a little bit of, it's a little bit linked, right? But we could imagine a net force that changes as a function of time. If we can express the force as a function of time, then we can integrate this because we've got a differential dt and a thing that is a function of t. So we could integrate both sides. And here I'll write that it is explicitly a function of time that we're talking about, equals the integral of d momentum. The integral of d momentum is momentum. Well, I guess it's delta momentum, right? We got a definite integral. Otherwise, we got to worry about an integration constant. I don't want to do that. Let's use a definite integral. We're talking about from condition 1 to condition 2, the momentum changes. In other words, we've got some momentum now, and we started with some other one. So the fundamental theorem of calculus just gets us P2 minus P1, which we've defined as delta P, delta momentum. These equal signs, this one here, this one, and this one. This is the equal sign that lives in Newton's second law. These things are equal. I'm going to use a different color just to kind of highlight what we're doing here. This equal sign is equal because Newton's second law. This equal sign, the equal sign that says that momentum is defined as mass times velocity, that's a definition. We declared that to be true, and if that is true, then Newton's second law says this, and this, and this. This is sort of a different quality to these equal signs. This expression, the time integral of force from T1 to T2. This is Newton's second law. It's always going to look like this. So we're always going to be doing this kind of an integral. We could sort of codify that. We can make that a thing with a definition. We could give it a name. The time integral of force, call it, I don't know. Just make something up. Make something up off the top of your head on impulse. Impulse. Let's call it impulse. Impulse is a thing that prompts you to move, and that's what we're talking about. An impulse is a thing that prompts you to action, to motion, And this is the combined effect of force applied to a thing over time such that it changes the motion. Impulse is not a terrible name for this. Let's define impulse as the time integral of a force dt. We're here talking about the impulse then as exerted by the net force. So we could talk about all right, there's a special case. If the force we're talking about is the net force, then I guess we're talking about, if we're going to use this definition, we're talking about the net impulse. This equal sign is as a result of the definition we made. There's nothing special about the word impulse. All we're saying is that the time integral of force, I want it to be named. I want it to have a name. And I want it to be named impulse. The symbol that I'd like to use for impulse is J. That's a capital J. And it is vector because the right-hand side is vector. Its unit is the same unit as the unit for momentum. If we're talking about sigma F, if we're talking about the net force here, we wanted to talk about the net impulse. So I'll use the summation symbol here. Maybe there are multiple forces acting. Each of them apply some impulse to an object. Together, they apply some net impulse. So, okay, so we've defined momentum. We've defined impulse. And we have so far modified the right-hand side of Newton's second law so that it looks differential with respect to momentum. But now we can modify the left-hand side. This integration here is a thing. That's the impulse. That's the net impulse. And Newton's second law says that it is related to the change in momentum. So let's write that here. I'm going to write that the net impulse is equal to the change in the momentum. This equal sign, it's not by definition. This equal sign is this equal sign because this side is net impulse and the right-hand side is change in momentum. This is the same equal sign that lives in Newton's second law. We haven't said anything new, is the thing. This is Newton's second law. We just dressed it up in different hats, basically. Oh, it's a time integral now, but it's still a relationship between between forces creating motion and the motion they create. Between impulse prompting motion and the motion they create. And it's Newton's second law that's doing the job of telling us that those two things are equal. Cool. That is segment 1. On to the next.